with both of these, the idea is you've got the parentheses and the thing outside multiplying it. So we're going to have to distribute, right? So we distribute this first one and the second one. We get, so 2 times 3, we got 6x. 2 times 5, so that's minus 10, equals 5 times x, well, that's 5x. 5 times 4 is 20. And here we have everything we need, right? Now we can just solve this equation. For those of you who are new, one of the things that I always make a point of talking about, when you've got an x on both sides, it's super duper important to make a choice. It doesn't matter which side the x goes on. I tend to prefer the left-hand side, but it doesn't really matter. As long as you get the x's on one side and the numbers on the other, it doesn't really matter. So let's subtract 5x from both sides just to make the choice of putting the x values all on the left, right? So I'm left with 1x minus 10 equals 20. Both sides to get x by itself, and I'm left with x equals 30. Hello, everybody. So I wanted to cut in here because I did make a mistake first hour when I recorded this, and I just wanted to go over and make sure that everybody was clear. Don't forget when you multiply through to distribute to both things. So if you do negative 2 times x, and you do negative 2 times 1, this should be negative 2 as well, right? So everything else was basically the same. I just forgot to put a 2 here and put a 1 instead because, 7:30 in the morning. But what you can see here, same idea, add the 2x to both sides. Then subtract the 15 over to both sides. And then you get 5x equals negative 17. Divide both sides by 5. And that's what you get, negative 3 and 2/5. All right, or negative 3.4, or just leave it as negative 17 over 5. Either way is fine. All right. Sorry. See you. What we are doing today is we are going to be using ratios and proportions to solve problems. So how are we going to do this? We're going to write out the proportion as an equation and solve. As we get into the idea of similarity, that's what this whole chapter is about. This is sort of the introduction. We're going to be using ratios and proportions a lot. And so it's really important to get this information down now. And a lot of this stuff you're going to see is going to kind of be old stuff. Like if you took Algebra 1, you should know how to solve a proportion. In middle school, they talked about ratios. But this is going to be geared a lot more towards the geometry type stuff. As you'll see, a lot of like, okay, well, the angles are in this ratio. What are they? Or the sides are in this ratio. What are they? Going with that information. So we're going to have a lot of those types of problems that we're going to be looking at. All right, so what is a ratio? A ratio is a comparison of two quantities, and usually, especially when we're talking about it written as a fraction, we are comparing them with division, right? So like if I went through and I counted, the number of men, the number of women, the number of non-binary people, and put them into a ratio. We'll talk about an extended ratio in a minute where there's more than two. We would have a numerical comparison between the groups that I've set aside, right? The key I want to point out here is that ratios are only meaningful when you let them be meaningful. So you usually are going to want to have the same units, right? Like, for example, when I was giving my example earlier about men to women to non-binary people, all three of those units are people, right? Or if I'm, comparing the dimensions of a room, that ratio really only makes any sense if you're measuring all the dimensions in the same unit. Like if you put one in feet, one in inches, and one centimeters, that's not going to tell you anything. So make sure that what you're doing is actually creating meaningful ratios. So let's move forward and do an example here. So what we have here is a picture. This picture right here is of a bonsai tree. A bonsai tree is basically just a miniature tree. It's a real thing. Uh, like somehow they cultivate trees to get smaller and smaller and smaller and smaller, and voila, you have this little mini tiny tree. Um, and oftentimes a bonsai tree is a miniature version of an actual tree that's like big. So here's what they're talking about in this problem. Um, a Florida bald cypress tree, that's a type of tree. And this particular one that they're talking about has a name, the Senator, and it's 118 feet tall. And we want to know what's the ratio of this bonsai version of the bald cypress tree to the Senator, right? So all we have to do is we have to write this as a ratio. Now you'll notice 15 inches, but the other one is 118 feet. And that don't work, right? We can't have inches to feet. This ratio right now as it stands is meaningless. So what I'm going to do is I'm going to take this 118 feet and I'm going to turn it into inches. If we want to go from feet to inches, all we do is multiply by 12, right? So we got 118 times 12. We just do our multiplication. 8 times 2 is 16. Carry the 1. And then times 10. And add. Right? So the actual ratio that we're looking at is 15 inches to 1,416 inches. Right? But one of the things, when we write a fraction, we want to make sure it's in simplest form. And if you look here, well, let's check to see if it's in simplest form. 15 has a factor of 5 and a factor of 3. 1,416 doesn't divide evenly into 5, right? That last number is not a 5 or a 0, but it does divide evenly into 3. And we know that a really easy way to check to see whether or not something is a multiple of 3 is if you take the digital root of the numbers. That is to say, you add them all together, and then you get a multiple of 3. So 6, 4, 1, and 1 is 12, right? Right, this whole thing here is 12. If you add these together. So you know that 1,416 actually divides into 3 evenly, which is nice. So let's do that. 3 doesn't go into 1. 3 does go into 14. 3 times 4 is 12. That's the biggest multiple of 3. Subtract, you get 2. Bringing this down, you got 21. 3 times what is 21? That's 7. Then bring down the 6. 3 goes into 6 twice. 0 remainder. We know that we divided it evenly, which is what we were sure we were going to do. So when we divide the top and the bottom by 3 to get simplest form, well, 15 divided by 3 is 5. And then 1,416 divided by 3 is 472. And so I will tell you that this 15 inches to 1,416 inches is a perfectly fine ratio. But I will warn you in advance, if you give Math XL this one, it will mark it wrong because it's not in simplest form. Math XL will expect 5 inches over 472 inches. If you know, or whatever your problem is, right? But they'll expect that. They'll expect that you check to see that it's in simplest form, and then they'll expect you to do it. So give this one a try. All right, let's go ahead and go over this. So it tells us, let's read this out, a bonsai tree is 18 inches wide and stands 2 feet tall. Again, notice inches, feet, different units. We can't have that. So let's take these feet and turn them into inches just before we even begin the problem, right? 2 feet is 2 times 12 is 24 inches. And by doing this in advance before you even bother starting the problem, now it's going to be so much easier to do, right? Because now all I have to do is say, okay, well, width to height, well, now I've got it. 18 inches to 24 inches. Now let's simplify this down. 18 and 24. If I look, I can divide the top and the bottom by 6. That'll get me 3 to 4. Now, if you don't see this 6 right away, like, okay, well, 18 and 24, they sure divide by 2. And you get 9 over 12. And then you go, oh, wait, also 3. I see now. Right? You can take as many steps as you need. I guarantee you, when I was first learning this, it took me the same amount of time. Because sometimes we don't see things immediately. Eventually you'll go through and you'll get it and you'll be fine and you'll see. But like, don't be afraid to take extra steps to make the problem easier to do in smaller chunks. It's okay to do that. All right, let's move on. Here's another one. Again, the same idea. We got to make a ratio. But now they're asking us sort of a different question, right? They give us the ratio as 2 to 3, and they tell us that there's a total amount. So they want to figure out how many of each type of flower that they need to get, right? So for every 2 tulip pots, they end up buying 3 daffodil pots, right? Well, what we can do is we can add up the ratio, right? We can say, okay, well, 2 parts plus 3 parts had better equal 120. Do I know what the number of parts is? Not yet, but I'm going to find it, right? So the way I like to do this is my way. And to me, I think it works, but like, you know, if there's a different way or the book explains it to you in a different way and you like that way better, please feel free to use that way. I will not be bothered. I will not be emotionally harmed by it. But I'll tell you, this is the way that I do it. I say, okay, well, here's my ratio. Well, I don't know how many parts I have, so let's call that X. So the ratio is actually 2X to 3X, right? Part and part. Well, now I know that if I add these parts up, I better get the amount that I want, right? The fact that I can do that, right? The number of tulip pots plus the number of daffodil pots had better add up to 120. So now that I've got this right here, I can make my equation. I can say, all right, well, 2x and 3x, that's 5x. And then I divide both sides by 5 to solve for x, right? The number of parts. So this won't be our final answer, but this will be a way for us to figure out our answer, okay? That's the important thing. X is not our answer. X is going to be how we find our answer. So we do 120 divided by 5. Okay, 5 doesn't go into 1. 5 goes into 12 twice. Drop down the 0. 5 goes into 24 times. So we get a final answer of 24. So now what we can do to figure out the number of each type of tulip, that's 2x. Well, what's x is 24, right? So what's 2 times 24? So the number of tulips is 48, right? Same thing here. I can do this. The number of daffodil pots was, I'm not going to write the whole word. I'm just going to do DAFF for daffodil. 3x. Well, 3 times, how many parts? Well, 24 parts. 3 times 24. What was that, 72? 6, yeah, carry the 1, 72. And at this point, you can say to yourself, well, how do I know I did it right? Well, if I did it right, what should these two add up to? 48 plus 72 had better add up to 120. Does it? 8 plus 2 is 10. 40 plus 70 is 110. 10 plus 110 is 120. So I know I did it right. Yeah? So this is the way I would handle this type of problem. I would first break it up into parts. Then I would make my equation and obviously solve the equation. But then I can go back and I can plug in and I can say, all right, well, for every 2 parts, I have 3 parts. Let's figure out the 2 parts. Let's figure out the 3 parts. All right. Now, this way works really well for me. It makes a lot of sense for me. Please feel free to use this method if you like it. If you don't like it, the book does have a couple other ways that they show, but it's all fundamentally the same thing. The book is going to somehow force you to obtain 2x plus 3x equals 120 anyway. This is just the explanation that really sticks in my brain personally. All right. So go ahead. Okay, folks, let's go ahead and talk about this one. So what we're saying is the measure of 2 supplementary angles are in this ratio. So this is basically the exact same thing as the last problem. The only difference is that they don't directly give you what they add up to, right? In this previous one, they specifically say the total is 120, right? But here, they say it to you in a way that you're going to have to understand. It says the measure of 2 supplementary angles, right? Supplementary angles, they add up to 180, just like we learned in chapter 1, right? So here, the ratio is 1 to 4. So we've got 1x plus 4x, right? So our one angle plus our other angle, they add up to 180. So all we have to do is we have to say, all right, well, what's x plus 4x? What's 5x? We got 5x equals 180. Let's divide both sides by 5 and solve for x. 180 divided by 5, if you believe me, is 36. I can do it on the side here. Right, 5 goes into 1 0 times. It goes into 18 3 times. right? 3 times 5 is 15. 8 minus 5, well, that's left over of 3, and then drop down the 0. 5 times what is 36, right? So 1 part is 36, but we don't want 1 part. We want to know about the angles. So let's look. What's angle number 1? That's 1x, right? So what's 1 part? 36. So we got 1 times 36. That angle is 36. What about the second angle? Well, we said that one's 4x, right? Well, what is that? 4 times 36. We do that out, we should get 144, right? Again, if you don't believe me, 6 times 4 is 24. Carry the 2. 3 times 4 is 12, plus 2 is 14. Voila, 144. So I wanna reiterate, yeah, we are solving for some x, but remember that x isn't our answer. That x is a tool to help us along the way. Basically, what we're doing is we're taking this ratio, and instead of simplifying it down into simplest form, we're scaling it up into something useful, right? So just be aware of that. Be aware of what is being asked. Be aware of what the final answer actually needs to be, though, right? 36 and 144, those are the measures of the angles. That is your final answer, not x. All right, so just be aware of that. Be very, very mindful. All right. So now we were talking earlier about extended ratios. I had mentioned them a little bit. I want to talk about them here now. It's going to be the exact same idea, but now it just, instead of 2 numbers that you're comparing, now it's 3 or more, right? My older example was men, women, non-binary people, right? You've got 3 different groups of people, and then you can compare them, right? Or, since we're doing math, we could be talking about the sides of a triangle or the angles of a rectangle or a pentagon or whatever, right? And if we're given these ratios, we can figure out the values, right? So let's go forward and talk more about this. So here, I was just talking about this. The lengths of the sides of a triangle are in this extended ratio. Now they tell us the perimeter. They tell us what the 3 angles add up to. So this is a lot like the flower pot one. They tell us the quantities in relation to each other. They give us the total, so we can figure out, well, if I've got 3 parts to 5 parts to 6 parts, they better add up to 98. So let's do that. 3 parts to 5 parts to 6 parts gives us 98, right? So I can go through, I can combine like terms. 8 and 6 is 14. Okay, so we got 14x equals 98. And so, I divide by 14. 14 times what is 98? Should be 7. So now I've got how many parts? So now I can actually calculate the lengths of my sides, right? Now I want to know what's the length of the longest side. So when I go through, my actual answer is going to be the one that's the biggest over here. Yeah. But just for GP, we're going to do all 3 just so y'all can see what I'm still doing the exact same thing, right? So 3 parts, which is 3 times 7. That's 21. This one was 5 parts. So just 5 times 7. Because 1 part is 7, right? 5 times 7 is 35. And we've got 6 parts. That's just 6 times 7. Well, what's 6 times 7? It's 42. So which one of these is my answer? It says longest side. So my answer is 42 inches. And, inches. How do I know that it's inches? Well, they tell us. The perimeter of the triangle is 98 inches. So if we're working in the same units, if this is 42, that had better be 42 inches. And again, if you are concerned whether or not you're correct, did I do it right? Well, go back and see. Do these 3 sides add up to 98 like they're supposed to? 1, 5, and 2. That's 8. Okay, we're on the right track. 2, 3, and 4. Well, that's 9. Hey, 98. So I did it right. Or at least I'm certainly in the ballpark, right? Always go through, double check all your work. It's important. Okay. Go ahead and give this one a try. Basically the exact same problem, right? The only difference is the numbers and the units. Okay, so let's go through. Once again, they give us the lengths of the sides and then they give us the perimeter. So they know what we know what this is supposed to add up to, right? 4 parts, 7 parts, and 9 parts had better make 60 somehow. So let's do that. 4 parts, 7 parts, and 9 parts make 60. So let's combine our like terms. 4, 7, and 9. 4 plus 7 is 11. 11 plus 9 is 20. So we got 20x equals 60. Divide by 20 to give us 3, right? So this is the value of each part. Well, now we want to figure out the lengths of the sides, right? Well, so we got to find all 3 of them. Last time they only asked us to find one. Here, we're actually being told we want to find the whole thing. So let's start off with the smallest one, right? Now we'll do the medium-sized one. It's supposed to be a 7. And then the biggest one. So here are our 3 sides. And again, it's the sort of thing where you go through and you say, all right, did I do that right? 2, 1, and 7, that's 10. Carry the 1. 2, 4, 5, 6, that's 6. 60. 60 centimeters. So what are the lengths of the sides? 12 centimeters, 21 centimeters, and 27 centimeters. Right? So just be aware, that's basically the easiest thing to do out of all this stuff. Seriously. All right. So let's talk about proportions. So a proportion is basically when you take 2 ratios and set them equal to each other. Basically, a fraction equals a fraction. And obviously, as we go through this, we're going to want to talk about if there's a variable somewhere up in there and how do we deal with that. So I don't like the means and extremes way that the book does this. I've never liked it. I think it sort of tries to make everything feel very magical. It's like, if you multiply the means and set that equal to the extremes, you have, and it's like, well, but why? So I wanted to make sure to talk about this, what's actually going on, because I don't want us to leave here thinking that this is magic. Cross multiply, yeah, sure, but what does that even mean? So here, this is what's going on, right? What you're doing is you're multiplying both sides by the least common multiple of the denominators here. Or really, you don't even have to do that. Just multiply both sides by both denominators. See what they did here? They multiply both sides by b times d, so that the b cancels out with the b on the left, the d cancels out with the d on the right, and then what's left over is what they have. So, and that's the big reason why what I did in the bell ringer was I gave you problems starting here. All those problems that you were given started at this spot, and then you solved to the end. So now I want to sort of take it back a step so that we can talk about, well, how do we get to that step? So here, what I want to be able to do is I want to be able to find the solution. What is X that makes all this happen, right? So there's a lot of ways to go about this, but here's what I'm going to tell you. Easiest thing to do is multiply both sides by these denominators to clear them out, right? Here, the X is going to go away. You're going to be left with the 4. Here, the 4 is going to go away. You're going to be left with the X, right? So you've got 5 times X equals 6 times 4. Or, leave it backwards, whatever. But still, the point is that's what you end up having when you do this. And what's 6 times 4 is 24. Then just divide by 5, solve for X, and get your answer. All right, we're going to divide by 5. 24 divided by 5. Well, that's in simplest form already. I would just leave it like that myself. I'm not going to do anything with that. But maybe they ask for a fraction. And so, okay, maybe they ask for a decimal. So you can look at this. You say, all right, well, what's 24 divided by 5? 5 goes into 20, right? 4 times. And then 4 out of 5, that's 8, right? You see what I'm talking about? 5 goes into 24 only 4 times. Drop down that 0. 5 goes into 40 8 times. And then we're done. All right. Let me move this over. You come over here. Okay. So now that we've done that, let's do this one. Same idea. We're going to multiply the expressions up here. All right. The 9 is going to come up here. The 3 is going to come up here. And, just like what we had in the beginning, right? Just like what we had in the bell ringer. Distribute. Here you don't need to distribute, but it's like just 9y, right? Subtract the 3y over. Then divide both sides by 6 to solve. Same thing. All right. Give this one a try. Okay. So once again, we're going to go ahead. We're going to rewrite this as an equation. So we multiply to both sides to get these denominators cleared out. We should have a 14 left here. We should have a 2 left over here, right? So we have, I'm going to put the A on the left side because I like it that way. 14 times 9. 9 times 4 is 36. 1 times 9 plus 3 is 12. And we can divide both sides by 2. We get 63. And again, if you look, 63 over 14, if we were to simplify that down, divide the top and the bottom by 7, we better get 9 over 2, right? Same thing here. We're going to go through cross multiply. It doesn't matter that the variables are on the bottom. It's going to be the exact same thing. Going to have 3 times m plus 1 equals 15 times m. Make that look better. And then we have to distribute. We can subtract the 3m over. And then we can divide both sides by 12. We end up with m equals 3 over 12. Divide the top and the bottom by 3. 3 divided by 3 is 1. 12 divided by 3 is 4. So we get our answer of 1 over 4. Okay. All right. We've got one more topic right here. And basically, all we're doing is learning how we can play around with these proportions. Basically, the idea is there are ways to switch the proportions around. And again, these are sort of hand wavy. The problems we're going to do are going to help reinforce that a little bit. So here's the idea. If you know your proportion as written, as long as you flip both sides, you can take the reciprocal of the left, the reciprocal of the right. So they give you the example right here. 2 over 3 equals 4 over 6. Flip it. 3 over 2 equals 6 over 4. Same thing. You can switch the means the way that they did it here. And the big reason is because they're getting multiplied anyway. So you can just flip the order of them. And it works the other way too with the extreme, that you can just switch them and then you don't change the value of the proportion. And then this one is really interesting, is that if you take the denominator and add it to the numerator on both sides, you also still keep the same proportionality. Okay? We can come back to this page in a little bit, but I want to actually physically show you. So here's the thing. You're going through and you've got a problem like this. They're asking you to complete the equivalent ratio thing. So you got x over 6 equals y over 7. Just notice what goes together. Here x goes with 6 and y goes with 7. So if I've got this rewritten over here, if x goes with 6, 6 is going to go over here, right? If y goes with 7, 7's going to go over here. And we'll talk a lot more about this picture later, but look at how it's set up. X over 6, y over 7. Do you see how the common parts line up? So if I do x over y, it only makes sense that this is going to be 6 over 7, right? So I'm not going to have you do this independently. I do want to sort of take the lead on this discussion because it's sort of I want to help motivate your intuition going forward. So I want to show you what's going on here. Same exact thing, right? 6 over x. Well, what goes with 6? 7, right? What goes with x? Y. So 6 over x had better be the same as 7 over y, right? Now with this one, x plus 7 over 7, look, or y plus 7 over 7, look. What's y plus 7? This thing, right? That whole thing. So what do we expect the corresponding thing from y over 7 to be? Shouldn't it be the whole thing over here? So shouldn't this be x plus 6 over 6? That's the one big reason I wanted to take the time to actually physically motivate these, because I don't think this is justified. They tell you that these are some things and they just sort of do whatever. But I don't like that. I don't think that it really helps to just say these things. It's much easier when you actually physically look at the diagram that goes with it so that you understand what they're talking about. Why are these things what they are? All right.